Today, we are diving into a world that, honestly, sounds like it's pulled straight from science fiction. We're talking about acoustic metamaterials. These are materials that are specially engineered to control sound in ways we used to think were completely impossible. I mean, really think about that. What if you could walk into a room and be totally silent? Not because you're being quiet, but because sound waves are literally bending around you, like you aren't even there. Well, that's the wild promise of this tech. To get how it works, we first have to do a quick refresh on how sound usually behaves. You know, sound, like any wave, moves through things, air, water, whatever, by creating these pressure fluctuations. And for centuries, we've understood that its behavior follows some pretty fundamental, predictable physical law. And a big one is this principle right here, Snell's law. It basically says that when a sound wave hits a boundary, say going from air into water, it bends, it refracts. But here's the key thing. In every single natural material we know of, that bend is always positive. The wave keeps moving forward. That's just because natural properties like mass and stiffness are, well, always positive. Or are they? And this is where it all gets really, really interesting. Scientists started asking this crazy question. What if we could design a material that just doesn't follow the normal rules of physics? A material that could actually force sound to do completely unnatural things. And here is what that rule breaking actually looks like. So in this simulation, you've got the sound waves coming in from the left. As they hit that metamaterial in the middle, look closely. They bend the wrong way. They actually refract backward. Now, this isn't some visual trick. It's what really happens with this new class of materials. So how on earth is this even possible? Well, the secret is right there in the name. That prefix, meta, it's Greek for beyond. And these materials go way beyond the properties of the stuff they're actually made of. So an acoustic metamaterial isn't special because of what it is. It can be made of plain old plastic or metal. Its real power comes from its architecture. The magic is all in its carefully engineered internal structure, which is made up of these tiny repeating patterns that are actually smaller than the sound waves they're meant to control. Let's just put this side by side for a second. Natural materials, they have positive mass density, positive bulk modulus. But metamaterials, they can be engineered to have negative effective values for both. And that's the secret sauce that lets them bend waves backward. So where natural stuff gets its properties from its substance, metamaterials get theirs from their structure. It's a total flip of the script. Okay, this idea of negative effective mass is gonna sound a little mind-bending. And to be super clear, we're not talking about literal negative kilograms or anything like that. Instead, picture tiny little resonating parts inside the material. They're designed to vibrate completely out of sync with the sound wave hitting them. So when the sound wave pushes on the material, the internal structure actually pulls back. It's this opposition that creates what we call an effective negative mass. And that's the key to all this crazy sound manipulation. Okay, so we've got the what. Now let's dig into the how. How do scientists actually go about designing these incredible structures? Well, it turns out there are a few really clever ways to do it. One of the fundamental building blocks is something called a Helmholtz resonator. The concept is super simple. You know how you can blow across the top of a bottle and get a tone? That's the idea. Each tiny bottle you see here is tuned to a specific frequency. By arranging thousands of them in a precise grid, scientists can create a material that effectively has a negative bulk modulus. It's a powerful tool for controlling sound. Another way to do it is with membranes. Check out this design. It's basically a grid of thin, flexible sheets, almost like tiny drum skins, and they have little weights attached. When a sound wave hits them, they vibrate. And by tuning those vibrations just right, engineers can create that bizarre negative effective mass property we were just talking about. Now this one might be my favorite. It's called a space coiling structure. You can see these super intricate, almost labyrinth-like channels built right in. When a sound wave enters this maze, it's forced to take a much, much longer winding path to get through. This basically slows the sound way down, giving engineers another really powerful way to bend and control it. And look, this stuff isn't just theory. The big breakthrough came back in 2000 from a study by Liu and his team. They took tiny lead balls, coated them in silicone, and created this resonant structure. The result? They got over 60% sound reduction at 400 hertz with a material that was just 2 centimeters thick. That was the first time anyone had experimentally proven negative mass density. It was a huge deal. And after that 2000 experiment, the floodgates just opened. You can see how fast things moved. By 2006, we had materials with negative compressibility. Just a year later, the first design for a 2D acoustic cloak. And by 2012, those cool space coiling structures were achieving negative refraction over a whole range of frequencies, which was a massive step toward making them practical. Which brings us to the application everyone knows: acoustic cloaking. What you're looking at here is a real experiment. That pyramid-looking thing on the ground, that's the cloak. When sound waves hit it, its structure perfectly guides them around the object that's hidden underneath, just like water flowing smoothly around a rock in a stream. To a microphone on the other side, it's like the object was never even there. The potential here is, well, it's enormous. We're talking about everything from actual stealth technology to next-gen noise cancellation for entire cities or airplanes. It could completely revolutionize medical imaging with super high-res ultrasound. The ability to precisely guide and focus sound energy just opens up a whole new toolbox for engineers and scientists. So, what's next? What's standing between these amazing lab demos and our day-to-day lives? Right now, the whole field is focused on getting past a few key practical hurdles. Yeah, the big challenges are pretty significant. A lot of these designs only work for a very narrow range of sounds, not for broadband noise. Making them can be expensive, and, scaling up a tiny little lab sample to coat the side of a building, that's a massive engineering challenge. Plus, you have to worry about the material itself absorbing energy and weakening the effect. But solutions are coming online fast, and a huge one is advanced manufacturing. Trying to build those crazy maze-like structures we saw earlier with traditional methods would be almost impossible. But technologies like 3D printing, they are an absolute game changer. They let researchers design, test, and perfect these incredibly complex architectures at a speed we've never seen before. And that brings us to the next frontier, which is even more exciting. We're moving away from passive materials that just have one set of properties and towards active materials that we can actually change on the fly. The ultimate goal is programmability. As researchers put it so well in a 2024 paper, they're creating materials with multiple stable states and advanced functionalities. So what does that mean? Imagine a wall that you could switch from being soundproof to acoustically transparent with just the flick of a switch. Or a material that changes its properties based on temperature or an electrical signal. This is where it's all headed. So we're gaining this unprecedented, almost unbelievable level of control over the acoustic world. This technology gives us the power to sculpt our soundscapes, to silence unwanted noise, to focus energy in ways we've never been able to before. And that leaves us with one last really big question. As we master this ability, what kind of acoustic world will we choose to build?